All right, this first video will not help you solve truss problems. This first video is just to try to get some vocab figured out and some things that we need to understand before we attempt to start to learn how to do truss problems. So I took some pictures from your book in case you don't have your book home with you. Shame on you. And we're just going to go through this real quickly on some of these vocab terms and things like this. So if you remember, one of the last things I tried to teach you was that these trusses or these bridges are supported by certain kinds of supports. There were two kinds. There were, and they're drawn a little differently. So there's little triangles that could support, like we have one right here. Those are called pinned supports that have a pin through it. And so a pin support doesn't allow the bridge to move this way or up and down. It doesn't allow it to move right or left or up and down. It's pinned. It's attached. The roller supports is usually drawn with a little circle. It's called a roller support. And it doesn't allow it to go up and down, but it does allow it to move side to side. So a pin support doesn't allow either of these motions, but a roller support doesn't allow it to go up or down, but it does allow it to go back and forth. And this is usually good because bridge materials can expand under heat and things like this. So it's good if this bridge can have a little bit of leniency to move kind of slightly back and forth a little bit, as opposed to being pinned on both sides and then maybe the bridge buckling in the middle or something like that. So these are the two types of supports that we could possibly have in our truss problems. And what that allows us to do, it allows us to be able to let's see, is this an eraser? Oh yeah, cool, I got an eraser on there. Okay, so that allows us to be able to write on what we call reactionary forces. So reactionary forces like Newton's third law. So whatever force, there's forces that are working down, there's reactionary forces that go up so that it doesn't fall down. And so for a pin support, you draw a reactionary force up and down like this, and you draw one right and left. And we're not going to put the arrowheads on there, which direction they're going at the time being. We're going to kind of figure that out a little bit later. But for a pin support, you'll draw two lines like this. And for roller supports, you'll just draw one line like this because it allows it to not go up and down. This one, the pin support over here, does not allow it to go right or left or up or down. So there has to be reactionary forces to stop it from moving in those directions. So a roller support has one reactionary force and a pin support has two. So that's going to be important as we kind of draw some pictures and try to figure some things out. Okay, so assumptions that we're going to make about solving all truss problems. Okay, and there's some reasons you might not think these are very important, but to make the math easier, and it's not going to make it all that easy. Truss problems are hard. But to make the math more simplified, we're going to have like 5 different assumptions we're making. We're going to assume that all members are perfectly straight, that we're not doing any curvy kind of arcs or anything like that. All loads are applied at the joints, so any kind of weights that are attached or pushing on the bridge or whatever would be attached to the joints. The joints are these places here. These are called joints, all the corner pieces. And then the things in the middle, the boards or whatever, those are called members. So we have some vocab. We have members, and we have joints. And we just also talked about reactionary forces. Okay? So these are the reactionary forces, these lines down here on the supports. We have the joints, or these dots on here, and then the members are all of these. That's a member. All these, every single board here is a member. Okay? In between two joints is a member. All loads will be applied at the joints. All joints are pinned and frictionless. Okay? All joints are pinned and frictionless. There's no other forces working on there for friction. You don't have to worry about any of that. Each member has no weight. We're going to assume that each member has no weight itself. Okay, which isn't true, but we're going to just assume that. Okay, that all the way to the bridge could all be applied, like maybe in the middle of the bridge or something like that. Joints can only experience tension or compression forces. So it could actually experience like twisting forces, but we're not going to talk about those. So tension and compression, we're going to talk a little bit about that in this lecture here also. Okay. So what we want to do first here is we want to learn about what we call static determinancy. Static determinancy. And basically that means is, can you, with math, determine, can you solve the truss problem? Can you solve the truss problem? Some truss problems you can't actually determine if it would work or not. You'd have to like do a real life experiment to see if it's going to work out or not. But some things you can mathematically determine how all the forces that are going to be on it. And what we want to do is just a quick little equation to determine if it can be solved or not. So a statically determinate structure, a structure that can be mathematically solved, you can determine by this equation right here. If you take 2 times the amount of joints, that's greater than or equal to the members plus the reactionary forces, then that is a problem that can actually be mathematically solved. So 2j greater than or equal to m plus r, if that's true, if this ends up being true, then the problem can be mathematically solved. Okay, so j is the number of joints, m is the number of members, and r is the number of reactionary forces. So we're going to use this equation here to do a couple problems here in our book to see if the problem, we're not going to actually solve the problem, we're just going to see if it is solvable. That's all we're going to do. Okay, hopefully you're with me on that. You can always ask questions in the Discord later. All right, next page. So we have 2j greater than or equal to members plus reactionary forces. There's our equation, okay, if you don't have your books with you. And so we're going to do 519 quickly. You can do these all on a different notebook or something later, but you're going to have to put it in your books later because you're going to have to turn in those books at the end of the year. I don't know how you're going to get it to me, but you're going to have to mail it to me or something, I guess. All right. Prove whether or not the following is statically determinate. Here's a truss. Here's a truss problem. Okay, and we want to know, can this be mathematically solved, or do we not have enough information or something kind of wrong with it so that we can't actually mathematically solve it? So we're going to take 2 times the number of joints. All right, how many joints are there? Okay, there's one there. There's one at B. There's one at C. There'd be one right here at those intersection of those members, and there's one right here. There are 4 joints. 2 times 4. We have 8. Is 8 greater than or equal to how many members? 1, 2, 3, 4, 5 members. 5 plus how many reactionary forces? Okay, how do you get reactionary forces? Well, you look at the supports. Here's a pin support over here. That means we have 1, 2 reactionary forces. Here's another pin support, which means we have 1, 2 reactionary forces. These pin supports don't allow it to move right or left or up or down. So every pin support always has 2 reactionary forces. So I have 1, 2, 3, 4 reactionary forces. 8 is 8 greater than or equal to 9? False. That is false. This is not a problem we can solve. We're not going to be able to mathematically solve that truss problem, so I guess that's pretty easy. You don't have to do that one. It's not statically determinate, not mathematically solvable. Okay. I'm going to erase. Let's see. Erase. Ooh, you know what? I think I can do this. This is faster, maybe. Yeah, I can just hit this button and erase a whole bunch of marks and stuff. I think if I hit that other button, it's going to erase my picture, so I'm not going to do that. Okay, so let's look at problem 520. 520. Each side of the Main Street Bridge in Brockport, New York, has 19 joints. So you don't even have to add them up. I've already told you. And 19 joints and 35 members. One side has a pin support. We'll say there's a pin support over here. And the other has a roller support. Okay, is it statically determinate or not? Okay, so the pin support has 2 reactionary forces, right? And the roller support has 1 reactionary force. Okay, so 2 times J, how many joints? 19. Is that greater than or equal to how many members? 35. plus how many reactionary forces? 1, 2, 3, plus 3. 2 times 19 is 38. Is 38 greater than or equal to 38? And that answer is true. So this bridge would be statically determinate. We could go ahead and solve this problem some other time. Okay, so we're just using this. We're using this equation right here to see if things are statically determined or not. Okay, good. Next, all right, prove whether or not the following is statically determinate. So this looks a lot like the picture we just had. I'll write my equation here again. 2j greater than or equal to m plus r. Okay, looks a lot like the problem we just had, except the only difference is instead of this over here being a pin support, it's now a roller support. So again, we had 2 times joints, and the joints was 1, 2, 3, 4. 2 times 4 is 8. Is 8 greater than or equal to the members? 1, 2, 3, 4, 5. 5 plus, this is a pin support, so it has 2 reactionary forces, and this is a roller, so it only has 1. Remember earlier, this was a pin, so it had 2. And so 5 plus 4 was 9, and that was not greater than or equal to 8. So now it only has 3. So 8 is greater than or equal to 8. That is true. So that is now solvable since we have a roller support on the right end. Okay, so how do we solve truss problems? We did talk about these the other day. All of the sum of the moments, which we use the word torques. All the torques need to equal 0, which basically means your counterclockwise need to equal your clockwise torques. Remember, clockwise torques were actually designated as negative torques, and counterclockwise torques were plus torques. But we're not going to use those signs. We're just going to do a table and calculate our clockwise and our counterclockwise torques, and we're going to make sure that those are equal. So that's part of how we solve. These are the things we need to do right at the beginning of a truss problem, so we can start solving the internal forces in each member. But the first thing we need to do is balance out the torques. We need to make sure all the rights equal the lefts. This is the summation of all forces in the x direction, horizontal. So basically rights equal lefts. This is clockwise torques equal counterclockwise torques. And this here is fancy language for ups equal downs. We need to make sure all of our ups equal our downs, all of our rights equal our lefts, and all of our torques are equal also. Okay. Now, all these again have signs. Right is plus and left is negative, and up is plus and down is negative. But we're not going to use those signs. We're just going to make little tables and make sure that they're all equal. All equal. Okay, let's go to our last page here. And because we have to try to understand this here. So what we're going to do eventually, we're going to do those 3 things that we just talked about. We're going to do these 3 things here at the beginning of a problem. And then we're going to go through every single member in the entire truss and try to determine whether that member is under what we call compression forces or tension forces. It's going to be one or the other, every single member. And we need to calculate the tension or compression force in every member of the entire truss. Yes, this is really bad. Hardest thing we're going to learn in POE, and I really wish I could have taught it before we went on this break, because everything else I think I can probably easily teach not being on break, but could be tough for us. So we'll be able to get through it, I think. Okay, so here is like, let's say here's a board that's in a truss somewhere. It's a member. Okay, and if this thing is under compression forces, then you can imagine, I think, what that is. That would be like squeezing it together, right? So you'd have a force coming in like this and a force coming in here. It's squeezing it together. Okay, so I think that probably makes sense, that is something under compression. Now, the problem is that we're not going to look at these forces on the outside. We're looking at internal forces inside a member. So what you have to remember is Newton's third law. Newton's third law says that for every force, there's an opposite force. working against the other way. So internally, if these are our external compression forces compressing, squeezing this thing together, internally the forces would look like this. They'd be opposite those. And those are the ones we're figuring out. So a problem when I'm teaching this has always been that if you are drawing your truss problems and you're looking at a member and you figure out the forces are going like this, you tend to look at those forces and think, oh, that looks like tension. It looks like it's pulling apart. And it's not. That's actually, the forces going away from each other like this are actually compression forces in that member. Compression forces. So the way I try to have people think about it is, don't think about inside the member. Think about the joints. Think about these joints right here. If you see the joints here and you see an arrow going right at the joint, then I think it makes more sense to say, hey, that joint is being compressed. Does that make sense? I hope. I hope so. I can't hear if you're saying yes or not. So there's a joint, and if the arrow is pointing towards the joint, then that's a compression force inside this member. And so this arrow is going this way. You're not going to have arrows going both ways inside this thing. This inside any member, you're going to either have this where the arrows are going outwards like this. That's compression. And by the way, there are going to be signs on that. A compression force is a negative force, and we are going to use those. We are going to use those. So any compression force you have, you're going to assign it a negative value. Okay? For like the ELABs and things like that. So if you determine the forces, internal forces in a member, and I'm going to show you how to do all this. I mean, you don't know how to do that right now. I understand. But just keep this in mind, that if you end up determining that the forces are going outwards in a member like this, that's actually a compression force and it's a negative. What if we have a member and there's external forces pulling it apart like this? Well, that's called tension. That's called tension. If you try to pull something apart, you would feel the tension inside that. Now we're looking again at the internal forces. So what would the internal forces look like? Well, they'd be equal and opposite to these external forces. So internally, you'd see forces that look like this, equal and opposite to those. So you're not ever going to see these forces out on the outside. That's the problem. You're not going to see these. You're going to determine what forces are inside. And if you determine that a force should be going this way and this way, that is called a tension. And it's confusing because it looks like they're going towards each other, so it looks like it's compressing. No, it's not. It's actually, think about the joints. Think about what it's doing to the joint. It's pulling on the joints. So it would be tension on the joints. So this is a tension, and that's going to be a plus sign. All tension forces are going to be plus signs. All compression forces are going to be negative signs. Here's the cool way to remember that. Tension. Aha, yeah, see, look at that. So tension starts with a T, and that looks an awful lot like a plus sign. Okay, so if you know you have tension force, you need to put a plus sign on it. What does a tension force look like? It looks like the arrows inside the member are pointing towards each other. That means tension. Okay, so that's a lot of stuff, and we're not basically any closer to solving the truss problems yet. That's going to be I'm not going to do one video. I think I'm just going to do one big problem, and I'm going to divide it up into several little videos to do the whole problem. So all that information you just learned is going to be kind of important to be able to understand what we're talking about when we actually start doing the truss problems. That was almost a 20-minute long video. Ouch. Okay. Well, hopefully you kind of understood some of that.